Welcome everyone. This is week 10. Okay, let me write 10. Okay. So this is week 10 of the tutorials for atomic and molecular physics, and we are approaching near the end of this course. So therefore it is not very surprising that the attendance has reduced monotonously, and here we are with nobody joining today. Anyway, it doesn't matter because this will be uploaded to YouTube, so you can always watch this on YouTube and get as much as you want. Maybe this will help you in solving some assignments and also in understanding some physics. Okay, so we will discuss some problems based on the material that was taught for week 10. Okay, which is mostly related to molecules. Okay, so we have more or less covered atomic physics part of the course, and currently we are studying about molecular physics, especially diatomic molecules. Okay, so we will solve some problems for diatomic molecules and related physics. So I'll wait for a few minutes maybe, so that if anybody wants to join the live session they can join. uh, Otherwise I will start solving the problems and then you can watch it on YouTube. Okay. So I'll wait for maybe couple of minutes. Okay. So yeah, I guess then we will start. Okay, so let me begin by writing the first problem. So here is the problem. Consider a system of two masses Okay, so this is the first problem. Okay, so what we are given is we are given two masses. Okay, two masses m1 and m2, and they are connected by a spring, and spring constant is k. So if we draw a diagram, it will look something like this. Okay, so this will be k, this will be m1, and this will be m2. Okay, so k, m1 and m2, and we have to find fundamental frequency of SHM. Okay, so we have to find what will be nu naught. Okay, so how do you solve this one? So to solve this one, we note that this is a two body system. Okay, and this is like diatomic molecules. That is why we are discussing this problem. This is like a diatomic molecule. where you can think of mass m1, where you can think of mass m1 as, let's say, atom 1, and mass m2 as, let's say, atom 2. If they are different, like for example, this can be a molecule of hydrochloric acid. So your m1 will be the mass of hydrogen, your m2 will be mass of chlorine. Okay, so this can be, for example, hydrogen and chlorine, and we can assume that the attraction between them is like a spring. Okay, so they are attached to each other, and we can assume that they are attached to each other with some spring, and the spring has constant k. Then what we want to find is what will be the fundamental frequency of such a molecule, or in this case just two masses attached with a spring. So for this we use concept of reduced mass. Okay, and this will simplify the analysis of their motion. So here we are. Okay, so the reduced mass, okay, so this effectively, so the reduced mass effectively represents the inertia of the system as if it were a single particle. Okay, it represents inertia as if it were a single particle, so it converts it to one body problem. One body problem. Okay, and how do you define this? So reduced mass mu is defined as m1 m2 divided by m1 plus m2. Okay, so this is how we find the reduced mass, and this accounts for both masses. Then the fundamental frequency mu naught, this is the fundamental frequency. Okay, and this depends on, so this depends on spring constant k, okay, which represents, for example, if they are atoms, then this represents stiffness. Okay, this represents stiffness of the bond between the atoms. So this is determined by k, the stiffness of the bonds. And then it also depends on mu. Okay, and the formula is mu naught. Okay. So mu naught is 1 over 2 pi under root k by mu. Okay, this is the formula. So this is the equation, and now we have already calculated mu. So substituting for mu, we get mu naught. This will be 1 over 2 pi under root k times m1 plus m2 divided by m1 m2. Okay, so let's see. Yeah, it matches with option B. So option B is the correct answer. Now, further what we can do is we can do special cases, right? Let's do some special cases. So, firstly, let us do single mass and a wall. Okay, so our system will look like this. So we have a mass m here. This is connected by a spring, and this spring is fixed here to a wall. Okay, so this cannot move. So how do we get this? Okay, so here, so this is just writing m1 will become m, and m2 will tend to infinity. Okay, so mass 2 will become so heavy that it will act as a wall, right? So it will not move, just like a wall. So then our mu naught, in that case, it will become 1 over 2 pi, and because m2 is very very larger than m, so what will happen is this m1 plus m2 will roughly be equal to m2. This becomes km2 upon m times m2, and this m2 m2 cancels out. So we get mu naught as 1 over 2 pi under root k by. Okay, and this is what we get for a single body problem, right? This is what we get for a single body problem. So we can say that, yeah, because our answer is true in special cases, which means we have higher chances of being correct. We can do another special case of equal masses. So this will be like a maybe H2 molecule. Okay, something similar to that. So it will have two masses and both will be equal. So here m1 will be m and m2 will also be m. So our new naught, this will become 1 over 2 pi under root k times m plus m divided by m squared. Okay, so this becomes 2m and m, and this will cancel out. So this will become 2 pi under root 2k over m. Okay, so the frequency has become, let me write this as mu naught prime or double prime, which is under root 2 times mu naught prime. So if we remove the wall by an equal mass, we increase the fundamental frequency by root 2 times, which is roughly 1.4 times. Okay, so yeah, these were some special cases, and of course we cannot take m as 0 because the denominator, it will just diverge. Okay, so with that, let's go to the next problem, which will be question number 2. Okay, so this is our second problem, and the problem reads that the result of oscillation of electric dipole moment. So we have an electric dipole moment, okay, of a molecule, and it is oscillating. Okay, so let's say we have a molecule, and these are like the atoms. Let's say this is the negative atom, this is the positive atom, for example hydrochloric acid HCl or something, and we get dipole like this. And this is interacting with external radiation, interaction with external radiation. Okay, and then the question asks is, so when this electric dipole moment interacts with external radiation, what is the result? Okay, so the result, that is what the question is asking us. Okay, so and these are our options. So X-ray, UV, microwave, or infrared. So I reckon this was taught in the class. Okay, okay, so okay. So first of all, we should note that molecules can absorb and emit radiations. Okay, that is why we see molecular spectra. And the frequencies of the radiations that they emit or absorb, that will depend on different types of molecular motions. When we talk about electric dipole moment of molecule, okay, so changes in dipole moment occur during vibrational motion. Okay, and of these vibrations frequency of these vibrations, they lie in the, and the frequency of infrared spectra, like they are very similar. Okay, they are very similar, so therefore infrared spectra is correct. So when your dipole moment interacts with external field, okay, so here let's say we have some external field E, and when these two interact, so the frequency that we get, the molecules, that corresponds to infrared region. Okay, and now what is the significance of this thing? The significance is that we can do infrared spectroscopy. We can do infrared spectroscopy to study molecular vibrations. So this is the advantage in which we can use the vibration of molecules. We can use the infrared spectroscopy to study molecular vibrations. Okay, let's go to the third problem. It will be question 3. Okay. What is this one doing? Okay, so this is our next problem which we are going to solve now, and what it asks us is to find the wave number nu by c. Okay, so wave number is generally denoted by this symbol nu bar. Okay, and it is inverse of wavelength, or frequency times frequency upon speed of light. Okay, So this is another way to express the frequency of electromagnetic radiation, and it is commonly used in spectroscopy. Okay, and this is how they are related. To find the wave number of vibrational absorption peak, we will use the same formula which we used in problem 1. Okay, so in problem 1 we used the formula for nu. If you remember, the formula was this, and then we substituted for mu in terms of m1 and m2. So we know that this is mu, and if we divide this by speed of light on both sides, we will get what we'll get we will get wave number. So we'll use these two equations. So this is equation 1, this is equation 2, and then we can simply write wave number mu bar. We can easily write this as, let's write as nu by c, or 1 upon 2 pi c under root k by mu, where both k and mu are given to us. So you can see that k is given to be 1000 newtons per meter, and mu is given to be 10 to the minus 26 kg. So let's plug in the values. 1 over 2 pi, 3 into 10 to the 8, right? This is what we have outside, and inside what we will have is 10 to the 3 over 10 to the minus 26. Okay. Okay, fine. So this will then become 10 to the 29. Okay, so this we can write 10 to the minus 8 over 6 pi, and then this becomes 10 to the 29, so we can write as 10 to the 28 times 10, so this will become 10 to the 14 into under root 10. Okay, so finally we have, let me write here. So finally what we have is root 10 over 6 pi. Let me take one more 10 here, and then this becomes 10 to the power 5. And now let us use calculator. Put in the value of 10 root 10. Okay, so we have 10 into root 10. This is 31.6, and then let's divide this thing by 6, and finally divide this thing by pi. So it becomes 1.677 into 10 to the power 5 per meter, which matches with option A. Oops. So which matches with option A. Okay. So let's do next one now. Next one will be question number 4. Question number 4. Let me have some water. Okay. So we are given some energy levels, one corresponding to J is equals to 2 and another corresponding to J is equals to 4. Okay. It is said that J is rotational quantum number and B is rotational constant. Okay. And we are talking about rotational spectra. We are assuming a rigid rotator and we have to find the energy difference. Okay, this is what we have to find out. Okay, so now note that this is about rotation. So rotation of molecules. Okay, and these rotations, they are quantized. So rotations of molecules are quantized and they can only occur at specific energy levels. Okay, for a rigid rotator, let's say, what is a rigid rotator? It is a simple model of a rotating diatomic molecule. Okay, so we assume that we have a diatomic molecule and the bond between them is rigid. Okay, like this. Let's say this is one atom, this is the, let's say, second atom, and they are connected by a rigid bond. Okay, so here you have one atom, here you have your second atom, and the bond between them is rigid. So this is the model that we are using. So this distance between them, this will not change. So for example, earlier we considered a spring. Now we know that for a spring, this distance can change. So this is like considering a very rigid spring with, let's say, infinite k. So then that it will not compress or it won't relax. So this is the model of a rigid rotator. Okay, now you can solve the problem of rigid rotator quantum mechanically, and you can get the energy states depending on the quantum number j. That is the whole crux of this problem. Okay, so the energy of each rotational level is determined by rotational constant b. Okay, this is given to us, and rotational quantum number, rotational quantum number j. Okay, so there you go. And what is the equation? So the equation is E of j is b times j plus 1, where j is an integer. Okay, where j can be 0, 1, 2, so on. Now so we are given two j's, right, and we are asked the energy difference 2 and 4. Okay, for j is equals to 2, we will get E2 as b times 2 plus 1. So this will be 3, 6. So this will be 6b. For j is equals to 4, E4 will be b times 4, 4 plus 1. So this will be 5 times 4 is 20, and 20b. Therefore, the energy difference delta E is E4 minus E2, which will be 20b minus 6b, which is 14b. So delta E is 14B, which is option A. Okay, so this is how you solve a rigid rotator problem. Now let's solve one based on selection rules. So this will be question 5. Okay, some transitions. Okay, so this is the next problem, problem 5, and it is showing some transitions. So you can see in the figure that we have some transitions and they are marked as ABCD, and they are for a pure rotational spectrum. Okay, and we have to identify the transitions which are not allowed. Okay, transitions which are not allowed. So we have to remove the transitions which are not allowed. Okay, and this problem can be solved using selection rules. Okay. So not all transitions between rotational energy levels are allowed. Okay, not all of them are allowed, and selection rules dictate which can occur. And this is decided by selection rule. And the rule is for pure rotational spectra, delta J should be plus minus 1. So this means that in rotation transition, the rotation quantum number J can only vary by plus 1 or minus 1. Okay? So J can vary by only 1. Either it can increase by 1 or it can decrease by 1, not more than that. So here for option A, we see that it is going from 0 to 1. So here delta J is 1. So this is all right. For transition B, here delta J is 2. For C, delta J is 1, and for D, delta J is 2. Okay, therefore B is not allowed and D is not allowed. So these two transitions, B and D, they are not allowed. So this means option B is the correct answer. Because here you can see the transition is happening for delta J uh, is equals to 2. Okay? And this is not allowed by selection rule. Okay? So B and D is the correct option. Okay, let's do the next one. It will be question number 6, I believe. Okay, so the question asks what is the degeneracy? Okay, for rotational quantum number J is equals to 1 for pure rotational spectra. Okay, so what is degeneracy? Degeneracy, all of us know what is degeneracy. So it refers to the number of states with same energy. Okay, it refers to the number of states with same energy. So if there are 100 states with same energy, then degeneracy is 100. And what we are asked is, what is this number of energy states that have same energy for J is equals to 1, where J is rotational quantum number for pure rotational spectrum. Okay. For a rotational energy level, degeneracy is given by 2j plus 1. Okay, and from where does it come? So this comes from different possible orientations of the molecule's angular momentum in space. Okay, so here J is 1, so 2j plus 1 is simply 3. Therefore option C. Okay. So we are done with 6, and we will solve a few more for about an hour. Let's see. So I'll write the next one now, which will be question number 7. Okay. drink some water before we start solving this. Uh, okay. So, what is the question asking us? So, they have one molecule HBr, okay, and then they are doing infrared spectroscopy, and they see that the lines are spaced. Lines are spaced 1700 per meter apart. Okay, and then we have to connect this to moment of inertia of the molecule. We have to connect these two things. Okay, so obviously then this spacing of lines, and we have moment of inertia, and basically the question is asking that what is the relation, how are these two things related. Okay, what does moment of inertia has to do with spacing of spectral lines? So we have to fill that space, we have to build that bridge, make that connection, and that is all we need. Okay, so how they are connected is the rotational constant, the rotational constant B is inversely proportional to I, is inversely proportional to I, which is the moment of inertia. So by measuring the spacing, we determine B, and then calculate I, using I h over 8 pi squared c times B. So this is the equation that connects moment of inertia to our rotational constant B. And how do you get B? We determine B from the spacing, which is given to be 1700 per meter. So okay, now other thing to notice, the spacing between rotational lines that is equal to 2b. Okay, so this implies 2b is equals to 1700. These two. Okay. And now basically what we will do is we will find b from here and substitute in this equation. So we can directly substitute for 2b. So this becomes I is equals to h over 4 pi squared c into 1700. Okay, and then we can substitute the values. So h is 6.626, 10 to the minus 34, right? This is 4, and this is pi squared. This is 3 into 10 to the 8, and this is 17 into 10 to the power 2. Okay, so this becomes 10 to the 10. So this will become 10 to the minus 44, 6.626 into 10 to the power minus 44 divided by, this becomes 12 into 17 into pi squared. Okay, so let us again pull out our calculator and start solving this. Okay, so this becomes 0.00329 into 10 to the minus 44. So we can write this as 3.29 into 10 to the power minus 47. So this is the moment of inertia which we wanted to calculate. 3.3, 10 to minus 47, which is option B. Okay, I forgot to write the units. Of course, the units are SI units, which is kg meter squared. Okay. Yeah, so this is our answer. Okay. Let's So let me write the next one. Which will be question number 8. Okay. In a rigid rotator of mass m, if the energy of the first excited state is 1.5 MeV, then the energy in the third excited state okay, like this. All right. So again we are back to solving rigid rotator problem. Okay, we already solved one problem before, and energy of first excited state is given to be 1.5 MeV, and we are asked about third excited state. Okay, what will be the energy of the third excited state? Okay, so we have solved this problem before also, and that was in problem 4. As in question 4, right? We know that energy EJ is given as B times J plus 1. Okay, where J goes from 0, 1, 2, so on. Now what we know is, for first excited state, EJ is 1.5 MeV and J is 1. Right? J is 1. So this implies j times j plus 1 will be, so this is 1 and this is 1 plus 1 2, so this is 2, or 2 times b is 1.5. So this is what we get. Now for third excited state, we don't know EJ, but we know that J is 3. So this implies J plus 1. This is 3 times 4. So 12. So this is 12. Okay. And therefore E3 will be 12B, which will be 6 into, because 2B is 1.5, so this will be 9. Okay, so E3 is equals to 9 MeV. So which means option C. Okay, so we used the energy level formula of the rigid rotator. So first excited state's energy was given to us, from where we find out the value of rotational constant B, and then once we know the value of rotational constant B, we can find the energy of any excited state. In this question we asked for third excited state, so J is 3, and we get our answer. So this was question 8. Let's do question number 9. Consider the molecule okay, consider the molecule C12O16 and CnO16. C12O16. Where Cn is an isotope. So this is an isotope of carbon. Now it is observed that So, pretty lengthy one. Let's break it into something understandable. Let's look at this step by step. So, first of all, we have two molecules. Okay, so we have two molecules. So, one molecule that we have is C12O16, and the other molecule has an isotope of carbon, but oxygen is same. So, CnO16, and we have to find that which isotope of carbon is this. So we have to find N. Okay, now what is the data given to us? So firstly note that we have performed a transition for j is equals to 0 to j is equals to 1 in both the cases. So in both the cases, j is equals to 0 to j is equals to 1. This is the transition. Following transition happens. Okay? J is equals to 0 to j is equals to 1. And then we note the absorption lines. Okay, what is the frequency? So they occur at certain frequency. So for C12O16, it is 1.153. Okay, so here it is 1.153, and here in the other one it is 1.102. It is 1.102. Okay, so we have performed same experiment on both molecules, but we are getting different frequencies in the absorption spectrum. One is slightly less. Okay, so the frequency of the isotope molecule, that is slightly less than the carbon 12. Okay. Another important thing to note is that the force constant is not affected. Okay. So for both the cases, we have same force constant. Okay. So let's write force constant is not affected. But what is affected? Because isotopes have different mass. Isotopes have different mass. This means mu is affected. What is mu? As we discussed in the first problem, when we have a diatomic molecule, we have two masses, m1 and m2. So we can convert it into a one body problem by using reduced mass. And when mass of one of the atoms will change, so of course our mu will change. Another thing to note that, again, let's write all these important points. So B is inversely proportional to mu. This is also what we discussed in one of the problems earlier, that B is inversely proportional to mu. Okay, and this B will help us in determining the energy of transitions for both the cases. Okay, so then B is also different. So B is also affected by this isotope. So B is not same. Mu is not same. B is not same. Okay. So now let us first calculate mu. Okay, mu for C12 O16. So this will be 12 into 16 over 12 plus 16. So let me calculate. Okay, so this comes out to be 6.857 and mu of CnO16, this will be n times 16 over 16 plus n. All right. So this is what we have. So next what we have is we have this transition from j is equals to 0 to j is equals to 1, and the frequency of this transition. So frequency of transition that is proportional to b, and we know that b is inversely proportional to mu. Okay, b is inversely proportional to mu, so both of them combined gives us that mu is inversely proportional to mu. Okay, therefore we can write mu. Okay, let's write in terms of frequency. So nu, okay, I'll write n, and here I'll write 12, and here I'll write n. So then their ratio, because we have written 12 here, so 16n divided by 16 plus n will come here, and 6.857 will come here. So what this implies is at 16n or 16 plus n, this is, okay, for 12 this was 1.153, and here it was 1.102. Multiply this by 6.857. Okay, let me find this out. 0.153, 1.102, 6.857. Okay, so this comes out to be 7.174. So then we can write 16n is 7.174 times 16 plus 7.14 n. And this implies that n is 7.174 into 16 divided by 16 minus 7.174. Okay, let me quickly find this out. So we have 7.174, multiply this by 16 and divide this by so this comes out to be 13.0052. Therefore, because n is a integer, so we can take n to be 13. We can take n to be 13. Okay. So, option C. Okay, so this was a little bit lengthy. So let's go back to this problem once more so that we understand what we were doing. Okay. So in this problem, we are given two sets of molecules. One is a known one, that it has carbon 12, and one is an unknown isotope of carbon, which we are denoting by Cn. Okay, so the problem is to find out what is n is. Okay, is it 13, 14, what is it? To do that, we have performed an absorption spectra, we have performed absorption spectroscopy, and we see that when the transition from j is equals to j is equals to 0 to j is equals to 1 is happening, we are getting different frequency for both the cases. For one case, the frequency for the known sample C12, the frequency is 1.153, but for the isotope, we see that the frequency has slightly reduced. Okay, so then what we do, we make note of all the observations. Okay, we make note that we are given two molecules, the transition is happening from j is 0 to j is 1, and we have written the frequencies. Then we write what we know, that what all quantities are affected. So it is given that force constant is not affected, and because isotopes have different mass, so mu will be affected. Also we know that the rotational constant b, that is inversely proportional to mu, and since mu is affected, therefore b is also affected. Finally, we make another note that this nu, which is the frequency, which is what we are measuring, that this is directly proportional to b, so it will be inversely proportional to mu. So this is the crucial step. This is the crucial step, and this allows us to relate mass. This allows us to relate mass to frequency. Okay, so here in the next step, you can clearly see that we have made a relation between the mass, which is the effective mass, and the frequency, which is nu. Once we have this relation, we will put the values of frequencies and effective mass. These values are determined experimentally, and the values of effective mass we just calculated above. Okay, and then we can solve for n. So this is just a straightforward solution. Okay, just very straightforward arithmetic, and we get n is equals to 13. So this implies, and this is a C13 isotope of carbon. Okay, so this was, I think, problem 9 or 10. This was 9. It was quite lengthy. Okay, let's do problem 10 now. Write the expression for 0-point energy of a harmonic oscillator according to quantum mechanics. Okay, so this is a short one. Okay, so we are talking about a harmonic oscillator and we are solving it using quantum mechanics. Okay, and the question is asking us for 0-point energy. Okay, 0-point energy. And so what is 0-point energy? Everyone should know this, but in case you don't, so I'll just write out what is this energy. So it is energy possessed by harmonic oscillator like a molecule, for example, okay, at absolute 0, okay, basically 0 Kelvin. So when there is no temperature, we are at absolute 0. So what is the energy possessed by our harmonic oscillator? So for a quantum mechanical harmonic oscillator, I turned off my video. For a quantum mechanical harmonic oscillator, for quantum mechanical harmonic oscillator, the energy is n plus half h nu. Okay, where nu is frequency of oscillation. And n can take values 0, 1, 2, 3 and so on. Okay, so at absolute zero, okay, which is the 0 point energy, our okay, for let me write 0 point energy. N is 0. This implies E0. This will be half h nu. This is the 0 point energy. Okay? When we put n is equals to 0. So you can see that even at absolute zero of temperature, that our oscillator or molecules, they still possess some energy. Okay? So they will have some vibrations because of quantum mechanics, not because of temperature. Okay, at higher temperatures, when we go into the classical regime, we know that the temperature is why our molecules vibrate, right? It is the thermal energy which makes them vibrate. But even at absolute zero, we have some finite oscillations. Okay, they are very small, they are very tiny, but they are there and they come because of quantum mechanics. You cannot explain that by classical mechanics. Okay, so this was question 10. Let's do question 11. Okay, the value of omega E. Okay, so let us focus, and hopefully this is the last problem for today. Okay, let us read the question carefully. So what we are given? We are given the value of omega E for H2 molecules is this much, and of omega E xe, which is the enharmonic term, is this much. Okay, note that they are using omega E, but you can see that it is nothing but mu by C. So this is wave number. Okay, omega E is nothing but wave number. Okay, so omega E is 440000 per meter, and omega E xe is 12300. 12000 per meter. Okay, and what we have to do? We have to find the 0 point energy of H2 molecule. So this is what we have to find out. Okay, so first thing is, why is this enharmonic term coming? So real molecules are not like perfect harmonic oscillators, of course. Okay, so this enharmonic term it is introduced as a correction. To the energy levels. Okay, so we have solved one problem for harmonic oscillator, but enharmonic sorry, but real molecules, they are not like perfect harmonic oscillators, because this is a real system, right? So to make our model better, we add an enharmonic term, and this is like a correction term to the energy levels, so that the solutions which we are getting, they are much more physical, right? Okay, so so this is first thing. Secondly, enharmonic term also affects the 0 point energy. Okay, so it is not that the 0 point energy is determined only by the harmonic term. Then we can simply write it as half h cut omega. But that is not true. So let's write the 0 point energy then. Okay, so let me write E0. So this will be half h nu and minus half h nu prime. Okay, so this is the enharmonic term, let's say. Okay, and now we know that our omega E is nu by C, so we can easily replace nu, and what we will have is half h c here it is 1/4 omega E minus 1/4 HC omega E XC. Okay, let's take HC common. So HC, and this becomes omega E by 2 minus omega E XC by 4. Okay, now let's see. We are given the values of omega E and omega E XC. So all that is left is to plug in these values. Okay. So this is 6.626 into 10 to the minus 34. Speed of light is 3 times 10 to the power 8. And inside we have, so that was 4, so it will become 2 minus, okay, 1/4 of 1200 will become 3000. Yeah, so basically 6.626 into 3 into 10 to the power minus 26, and this will be multiplied by, so if we subtract, so this will be 217000. Yeah. All right, so this becomes 6.626. Let me multiply by 3. So this becomes 1, 5, 6. And this becomes 10 to the power minus 23. Okay, let me pull out my calculator. Okay. So this comes out to be 4.3 10 to the minus 20 joules. But unfortunately it does not match any option, so I think there must be a typo, and this should be the correct answer. So let me then change these numbers. 20, 20, 20, and now it's better. Okay, yeah. So, hmm, so this is our 0 point energy, and you can see that this is really very small. Like, okay, so yeah, that's time. Thanks for watching. If you have any doubts, put them in forums or put a comment on YouTube. I'll try to answer. Okay, again, thanks for watching. See you next Saturday, 3 to 5. Bye bye.